This is an intro to Unit 6, which is all about right triangles and trigonometry. We will have 2 units over trigonometry, basic right triangle trig, and then we'll do the more advanced general angle trig. So this is lesson 5.1, property of right triangles. So the first thing is, the property that most of you already know is called the Pythagorean Theorem. The Pythagorean Theorem says if triangle ABC is a right triangle with hypotenuse AB, then AC squared plus BC squared equals AB squared. The hypotenuse is always the side that's by itself. It's the longest side, so it's always the side that's by itself. The Pythagorean Theorem has over 100 proofs. There are very neat ones. One of the neatest, which involves area, is a link that's in the comment box of this YouTube video. I would like you to pause this video right now and actually check out this proof. So, the Pythagorean Theorem has a neat proof using area. Now, how do we use it to find area? So, here's an example of the use of a Pythagorean Theorem. It wants us to find the area of an isosceles triangle with leg length of 18 feet and a base of 30 feet. My picture is not drawn to scale. It normally isn't, but we want to use our geometry knowledge anyway to solve this problem. So what does our geometry tell us? Well, first off, height is the same as altitude, so we should be able to draw the altitude in from the vertex angle straight down and perpendicular to the base. In an isosceles triangle, the altitude is the same as its perpendicular bisector. Thus, we can say the base is split into congruent parts. So we can say that each of these bases are 15 feet. Now the question is, we need to find the height in order to find the area. Area, remember, is base times height, or 1/2 base times height for a triangle. So to find the height, all we need to do is use our Pythagorean Theorem. So using the Pythagorean Theorem, if I call this height h, we would have 15 squared plus h squared equals 18 squared. So 225 plus h squared equals 324. Subtracting 225, you end up with h squared equals 99. And then square rooting, h is the square root of 99, which is 3 root 11. So our area would be 1/2 times 30 times 3 root 11. 1/2 of 30 is 15, times 3 is 45 root 11. You will have to use simplified square roots, not decimals, for this unit, so please get in the habit of simplifying your square roots. Okay, this is interesting and all, but you likely learned this in middle school. What is the new stuff that we can learn from the Pythagorean Theorem? Well, one thing we can talk about is some shortcuts using the Pythagorean Theorem. We have a Pythagorean triple. What a Pythagorean triple is 3 whole numbers which satisfy the Pythagorean Theorem. So some examples are 3, 4, 5. Notice I always write the hypotenuse as the last one. Or 5, 12, 13. Or 8, 15, 17. Or 7, 24, 25. There are actually many, many more Pythagorean triples, and Pythagorean triples are one of those things that mathematicians and computer scientists are always trying to find the next Pythagorean triple, kind of like they're always trying to find the next prime number or the next digit of pi. I personally don't memorize any other Pythagorean triples than these, but these are nice to know. So how do you use these Pythagorean theorems to help simplify problems? Well, let's take a look at this triangle right here. We could just go through the Pythagorean theorem blindly to find x, or you could recognize that there's a Pythagorean triple in here. This is a 5 and a 4, so we should say that we are probably missing a 3. So the x is probably 3, and then noticing that the 5 and the 4 both have root 3, x is going to be 3 root 3. A shortcut way to find the third side. Here's another type of problem. In this problem, we notice that there's a pattern here. You might notice that 55 is the same as 5 times 11, and 77 is the same as 7 times 11. So we could shorten our work to do y squared plus 5 squared equals 7 squared. If we do that, we get y squared equals 24. So y equals 2 root 6. But that was the y that's abbreviated. So really, this third side would be 2 root 6 times 11, which is 22 root 6. It saves us from having to deal with really large numbers. How about this problem? Well, I notice there's a 3 and a 5, so I might say that the z is 4. However, there's a mistake there. Why is there a mistake there? Well, z is the hypotenuse, so it should be the largest number. So this is a problem where you need to be careful about trying to use Pythagorean triples. Pythagorean triples are not helpful in this problem. You're going to want to say 3 squared plus 5 squared equals z squared, which means that 34 equals z squared. So z is the square root of 34, and that cannot be simplified. So there are some neat things you can do with Pythagorean triples. They often help you to shortcut problems. Now, we know the Pythagorean theorem is true. Is its converse also true? Well, yes, it is. The converse would say if a squared plus b squared equals c squared, then the triangle is right. So that's nice and helpful for us because then we can determine if our triangles are actually right triangles. So we can do something like this. Determine if the triangles are right. Well, first the question is, how do we know which is A, B, or C? C is always the hypotenuse, so it should always be the long side. So in this case, 13 is C. Does it matter what I make A and B? No, because they're both legs. So 5 would be A and 12 would be B. So if I use my Pythagorean theorem, is A squared plus B squared equal to C squared? Well, is 5 squared plus 12 squared equal to 13 squared? Hopefully you recognize that this is a Pythagorean triple, and we do get 169 equals 169, so this is a right triangle. How about 6, 2, and 3 root 5? Well, the first thing you're going to want to do is figure out which one is C. So you want to look at what is 3 root 5. If I do 3 root 5 in my calculator, I get 6.7. So it's going to be my hypotenuse. So then I'm going to ask myself, is A squared plus B squared equal to C squared? So is 6 squared plus 2 squared equal to 3 root 5 squared? 6 squared plus 2 squared is 40. How do I do 3 root 5 squared? Well, I have to square each part. 3 squared is 9 times square root of 5 squared is just 5. So I get 40 equals 45. This is not true, so we're going to say not a right triangle. But what if it's not a right triangle? Does that tell us whether it's acute or obtuse? We know when c squared equals a squared plus b squared, we have a right triangle. Now, what about if c squared is not equal to a squared plus b squared? How do we know what type of triangle we have? Well, let's look at an example. Let's look at an example like this. If the hypotenuse is too small, it's going to pull the legs in towards it. And so this is going to be an acute triangle. So when we say that c squared is too small, it would be less than a squared plus b squared. And that would give me an acute triangle. If I look at a hypotenuse that is too long, it would pull the legs out towards the end points, which means that c squared would be bigger than a squared plus b squared, and it would be an obtuse triangle. So how do we use this in practice? Well, let's try a couple problems. So let's figure out first whether these side lengths actually create a triangle, and then if we know it creates a triangle, let's check to see if it's acute, right, or obtuse. So how do we know if side lengths create a triangle? You have to use the triangle inequality. But before we use the triangle inequality, we're going to want to label our A, B, and C. C is always the long one, so C in this case would be 28, so I'll call A 20 and B 21. So for the triangle inequality, we know that two sides have to be bigger than the third. Really, you only have to test the largest side. Is 20 plus 21 bigger than 28? Well, that would be 41 bigger than 28. That is true. So this is a triangle. You really only have to test that the two small sides, when they add together, are bigger than the large. Because if you add the large side to anything, it's going to be bigger than the small ones. Now you have to use the Pythagorean theorem to see what type of triangle it is. So we want to know, how does a squared plus b squared relate to c squared? So if I look at this, how does 20 squared plus 21 squared relate to 28 squared? 20 squared plus 21 squared is 841, and 28 squared is 784. So I see that 784 is smaller than 841, so our hypotenuse is not big enough. It's too small. So if the hypotenuse is too small, it means we have an acute triangle. Okay, let's try another one. 10, 12, 30. First thing we want to do is label A, B, and C. So 30 would have to be C, so let's let 10 be A and 12 be B. We need to try the triangle inequality. And we really only need to test that the two smalls, 10 and 12, are bigger than 30. Is that true? Well, 10 plus 12 is 22. Is that bigger than 30? No. So this is not a triangle. It's really important you test to see if it's a triangle first, otherwise you're wasting your time. All right, last one. 4, 6, and square root of 8. What is the largest of these? Well, square root of 8 is 2.8. So it appears to me that 6 is going to be my C, and we'll call 4A and square root of 8B. First thing we want to do is triangle inequality. So is 4 plus square root of 8 bigger than 6? Well, 4 plus square root of 8 is approximately 6.8, so that is true. So this is a triangle. Once we've tested to see if it is a triangle, we need to do the Pythagorean theorem to see what type. So we're trying to see how a squared plus b squared relates to c squared. So in this case, 4 squared plus square root of 8 squared, how does it relate to 6 squared? Well, this would be 24, and 6 squared is 36. So when I look at this, 36 is bigger than 24, so my hypotenuse is too big, which means we have an obtuse triangle. How might we use this in the real world? Well, here's an example that I've actually dealt with before. You're trying to set up a volleyball net to stabilize a pole. You have to tie one end of the rope to the pole 7 feet from the ground and the other end of the rope at a stake that's 4 feet from the pole. The rope between the pole and the stake is about 8 feet 4 inches long. Is the pole perpendicular to the ground? You really do want the pole to be perpendicular, otherwise your net is going to be all messed up. So what you want to do is test to see if it's a right triangle. So here's your net. You have a pole, you have your wire, and you have how far away it is. So we already said the pole is 7 feet. The stake is 4 feet from the pole. So this is 4 feet. And the rope is 8 feet 4 inches. We need to convert that into feet. 4 divided by 12, so this is 8 1/3 inches. Okay, so we want to test if this triangle is a right triangle. So we're going to compare the sides. We want to see if 7 squared plus 4 squared, how it relates to 8 1/3 squared. So 7 squared plus 4 squared is 65. 8 1/3 squared is approximately 69.44. So we would say that the hypotenuse is too big, which means that this triangle is obtuse. Well, it's definitely not right, but more specifically, it is obtuse. So if I wanted to bring my obtuse triangle to a right triangle, I would have to bring that pole in, which means I should shorten the string, the rope. Okay, when you come back tomorrow, we will talk about special triangles. I would like you to try the worksheet. It is posted on my calendar, so you could print it and try it if you want to try to get ahead. I would recommend that because we are going to move fairly fast. So if you have any questions, please write them down and bring them into class the next time I see you.